The question number 6 is the ratio of the de Broglie wavelength of alpha particle to that of a proton being subjected perpendicular to the same magnetic field so that the radii of their paths are equal to each other. Now it's given that radius of the alpha particle and the radius of the proton should be equal. In uniform magnetic field which is perpendicular to the path, a radius is equal to mb by qb, that is equal to momentum divided by the charge and the magnetic field. So we'll fill up here P alpha divided by Q into magnetic field, that is equal to P protons divided by charge of the proton into beta. Therefore, P alpha divided by P proton is equal to charge of alpha particle divided by charge of the proton, and this is equal to 2Q by Q, which is equal to 2. Now, the ratio of the de Broglie wavelength, the de Broglie wavelength lambda of alpha to lambda of the proton is equal to h upon p alpha divided by h upon p for the protons. So the p for the protons divided by p by alpha, and from this equation pp by this is equal to 1 by 2. Therefore, answer to this question is option number 3. The question number 7 says the anode voltage of a photocell is kept fixed. The wavelength of the light falling on the cathode is gradually increased. Then the plate current of the photocell varies according to this photograph. The current versus wavelength is given, and it is given that anode voltage is kept fixed. Now dear student, you know that the current is independent of the value of the wavelength till a threshold value is there. At threshold value, that is at maximum wavelength, no photoelectron emission occurs. So the current should be steady till you get the maximum wavelength where emission stops. So the correct option to this is option number 3. Let's go to question number 8. A 10-watt line source emits monochromatic light of wavelength 4000 angstrom when placed 1 meter away from the photosensitive surface. It liberates photoelectrons from the surface. When the same source is moved 2 meters away from the surface, the number of photoelectrons liberated reduced by a factor of. Now dear student, this is the line source, and from the line source there is a surface which is at a distance of 1 meter. Now he says that from this surface the line source is moved away to a distance of 2 meters. Now you know that the intensity in case of line source varies by the formula I is 1 upon T. So when you increase the distance, the intensity decreases. And also the intensity is proportional to the number of photons striking per unit time. If you're combining these results, when you increase the distance to double, so therefore the intensity will become the half. If intensity is half, the number of photons striking per unit time will reduce by a factor of 1 by 2. So n by t number of photon is inversely like this. So when you increase the distance from 1 to 2 meter, the number of photon per unit time will become 1 by 2. So it reduces by a factor of 2. So answer correct is the third option. Now let's go to the question number 9. The ratio of the de Broglie wavelength of the molecules of the hydrogen and helium in two gas giants kept separately at temperature of 27 degrees centigrade and 127 degrees Celsius is. Now dear students, these are the molecules and the wavelength h upon 2, the mass and the kinetic energy, but the kinetic energy for the molecule is equal to 3 by 2 k into T, k Boltzmann constant. So lambda is equal to h upon 2m into 3 by 2 kt. Therefore the formula becomes h divided by 3m kt root. Now in the first case it was hydrogen, so wavelength for hydrogen is equal to H divided by 3, the mass of the hydrogen, into K into the temperature. The temperature of hydrogen is 300 Kelvin. And for the helium, H divided by 3, the mass of the helium, into K, and the temperature is 400, right? The ratio of the wavelength of the hydrogen to the wavelength of the helium will be equal to the mass of the helium into the temperature of the helium 400 divided by the mass of the hydrogen into 300 root, right? Now fill these values. This is equal to mass of the helium, the 4 into 400 divided by hydrogen is 2 into 300. So this cancel out. It is equal to 8 by 3 root. So the correct option is the fourth answer. Let's move to the next problem. The work function of a photosensitive material is 4.2 electron volt. The wavelength of incident radiation on the cathode of this material, for which the stopping potential is 2 volt, lie in X-ray region, ultraviolet, visible, or infrared. Now dear student, the work function is given equal to 4.2 electron volt, whereas the stopping potential is given equal to 2 volt. So then this E into V kinetic energy will become equal to 2 electron volt. And by Einstein equation, the energy should be equal to 4.2 electron volt plus 2 electron volt, that is equal to 6.2 electron volt. Now, corresponding to energy, the wavelength Hc by lambda is equal to 6.2 electron volt. To find the wavelength Hc in terms of angstrom, we can find this is 12400 divided by 6.2, the answer in angstrom. And if you divide, this comes to be 2000 angstrom. And the wavelength 2000 angstrom lies in the ultraviolet region. Therefore, the answer to this question is answer number